All right, so we want to talk about polynomials. So polynomials are built out of monomials. So in this section, we're going to generalize some notation that we've talked about in the past. So we have a linear equation, and when we were talking about linears, we wrote them in the form f of x equals mx plus b. And we all agreed that m represented the slope and b was the y-coordinate of the y-intercept. Then in chapter 3, we were talking about quadratics, and they had the form f of x equals ax squared plus bx plus c. And we all agreed that a was the coefficient on the x squareds, that b was the coefficient on the x, and c was the constant term. Well, for quadratics, it worked out to use the alphabet ABC in alphabetical order because we knew quadratics had exactly, at most, 3 terms. Well, polynomials in general can be as long as we wish, so we have to change our notational strategy. So for a polynomial, we are going to write the following, which is f of x is equal to an x to the n plus a to the n, a sub n minus 1 x to the n minus 1 plus dot 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 all the way down to a2 x squared plus a1 x plus a0. And I know you're looking at this like, hold on, this notation seems a little out there, but it actually makes sense. So as we talked about with quadratics, since we knew it had 3 terms, we could use A, B, and C, the first letters of the alphabet, the first 3. We could go from front to back. The problem with polynomials, since we don't know how long or how many monomials the quadratic is going to have, our naming strategy, instead of going from the front to the back, goes from the back to the front. And we label the coefficients by the corresponding degrees. So the degree of a constant is 0. The degree of a linear is 1. The degree of a squared is 2. And remember, the degree of a monomial is the exponent on the variable. So we start by naming them in this direction. So we then can use this strategy to count all the way up to the largest termed monomial. So a quadratic in this notation is f of x equals a2 x squared plus a1 x plus a0. So writing it in this notation, we're basically saying when we look at this, if I want to know what the coefficient on the x squared is, what's the name of my coefficient? A sub 2, where the degree is the same as the subscript on the coefficient. So if I wanted to name the coefficient on the 10th degree term, I would say a sub 10. It just gives us a rational way to organize these things, counting from the smallest to the largest, because we don't know what the largest one could be. Because in theory, it could go on to be 100 million. We're not going to see any that big, but you could have a polynomial with 100 million monomials in it, and that's perfectly fine. So the next thing we want to take note of is the term a sub n x to the n, that is the monomial with the largest degree, is called the leading term. So our leading term has two parts to it that we're going to be concerned with. One is the degree, and the other is the lead coefficient. So if I were to ask the following question, well, what is the leading term if I have f of x is equal to 6x squared plus 17x to the fifth minus 2x plus 1. If I wanted to know what my leading term is, I would need to inspect the degree of each of the terms. So what is the degree of 6x squared? Well, that's degree 2. What's the degree of 17x to the fifth? That's degree 5. And what's the degree of negative 2x? Well, that's degree 1. And the degree of a constant is always 0. Perfect. So then, the leading term is the monomial with the largest degree. So which one's my leading term? Is 17x to the fifth. All right, let's take a look at one more. And I'm going to warn you in advance, I am trying to trick you in the next one. So what if I have f of x is equal to x cubed plus 3x squared plus 3x plus pi raised to the 20th power? All right, so we look at this. The degree of our x cubed is going to be degree 3. The degree of 3x squared is degree 2. The degree of 3x is degree 1. But now the question is, well, what's the degree of pi to the 20th power? Well, it's a constant. Does pi to the 20th power ever change? No. And what's the degree of a constant? 0. When we're talking about degree, the variable, the exponent has to be on a variable. Pi isn't a variable. Pi is the number 3.1415926. It never changes. So if something's a constant with an exponent, it doesn't matter. It still has degree 0. So then this would be our leading term, would be x cubed. So don't let something like that trick you. All right, so this leads to our first theorem in this section. And that theorem is going to go along with this chart-looking thing in your structured notes. So our theorem is called the leading term test. And the leading term test tells us about the end behavior. So if you're ever asked to describe the end behavior of a polynomial, the leading term test is the tool that you're going to need to use. So the leading term test states the following. If a sub n x to the n is the leading term of a polynomial, then the end behavior is given by the following. And I'm going to grab this diagram so that we can write on it. So we have what this is going to be is a flow chart or a choice chart. So we have our leading term is an x to the n, and it's going to depend on these things. So we have our n, or our degree, and that's going to be broken down into two cases. N is even, or n is odd. And then the next thing that we're going to be concerned with is if a sub n is positive or negative. So if a sub n is bigger than 0, or if a sub n is less than 0. So then the way our chart is going to work is if n is even and a sub n is positive, our end behavior is going to look like this. So our graph is going to start up and it's going to end up. If n is even and a sub n is negative, our graph is going to start down and it's going to end down. So those little squiggles that I'm writing in the middle are saying this theorem only tells us about the end behavior. It doesn't tell us what's happening in the middle. It gives us no information about that. All right, our bottom two branches, if n is odd and an is positive, our graph is going to start down and it's going to end up. And if n is odd and a sub n is negative, our graph is going to start up and it's going to end down. So these are the four possible end behaviors for any polynomial. It can start up and end up. It can start down and end down. It can start down and end up, or it can start up and it can end down. Those are the only four possibilities. So every polynomial will end in one of these four ways. And the way we determine it depends on the degree, which is our n, and the sign of the lead coefficient. All right, armed with this information, we are now ready to do example number 1. So we wish to sketch the end behavior of this graph. So in order to do so, the first thing we need to do is identify our leading term. So what is our leading term? Well, our biggest exponent on a variable, so remember, pi is a constant, so our leading term is negative 5x to the 12th. And we need our n and our a sub n. So our n is our degree, so that's going to be 12. And our a sub n, I wanted a highlighter, not a pencil. There we go. Is this. So we get our two things. A sub n equals -5, and we have n is equal to 12. So now we go and we look at our chart. So our n is 12. Is 12 an even number or is 12 an odd number? Well, 12 is even, so we go up to here, and then a sub n is -5. So is a sub n a positive number or is a sub n a negative number? Well, it's negative. So then that means our n behavior is going to look like this. Our graph starts down and ends down. So that's going to be the n behavior of our graph. So we have that this is a sub n was less than 0, and n equals 12 we had was even. And then we just select the appropriate picture, or if we were doing this by hand, we would sketch that appropriate picture. All right. Example 2 says, using a graphing calculator, estimate the real zeros, the relative maxima and minima, and the range of the polynomial function f of x equals x to the 6th minus 6x cubed plus the square root of x. So for this one, we explicitly are told to use our graphing device. So we go to our y equals, and we go x to the 6th power, so x, our caret key, and then 6. Don't forget to press your right arrow to pop out of your exponent. And then we go minus 6x cubed, and then plus the square root of pi. And pi is the secondary function on your caret key over here. So we go ahead, type that in, and we press graph, and our calculator is going to think for a second, and it gives us a picture that looks like this. And we were asked to find some of these things. So I'm going to blow this up a little bit and highlight a few important points. So we were asked to estimate the real zeros. So graphically, remember, zeros are the same as the x-intercepts. So zeros and x-intercepts are the same point. So that's these two things. And then to find our relative max and min, we see down here we're going to have a minimum right here. So we can see all of these things on our graph. So now the question is, how do we use these to answer the question, and how do we find them? The very last thing we want to do is find the range. Well, the range is going to be from where? From our minimum down here, whatever it is. So this is going to be our smallest y. And then it's going to go up forever, so to infinity. So these things are going to be a little bit related, and finding the minimum and the smallest y will help us find the range. So we can do all of this on our graphing device. So remember, it's been a while, but way back in Chapter 1, Section 5, we figured out how to find zeros with our graphing calculator. We found those in the Calculate menu here. So if we go Second and Trace and open up our Calculate menu, we'll notice choice number 2 says 0. And then later on in Chapter 2, we also used our graphing calculators to find maxes and mins, which we can do once again. So let's first go ahead and find our zeros, or our x-intercepts. So we select choice number 2, and then we have two different zeros we need to find. So the first one says left bound, and so I look at my graph and I'm to the left of that 0, so I press enter. And then right bound, I press my right arrow until my x value is to the right of that x-intercept, which it is. And then it says guess, so I move my cursor back closer and press enter, and my calculator will approximate that first 0 for me. Now the first 0 found on my calculator is 0.677. So the second 0, that's going to be this guy over here, we're going to rinse and repeat. So we go Second, Trace, to open our Calculate menu, we choose 0, and I'm going to move over. I am to the left of that 0 still, so I press enter. And now I need to move my arrow over till I'm to the right, which I am. So I press enter, and then guess, I move back closer, I hit enter, and my calculator gives me the approximation of that other 0. Which in this case is about 1.78-ish. So now we have our two zeros, so 0.6779 and 1.785-ish. The last thing we need to find is the minimum. So we're going to go back into that same menu again, Second Trace, but this time we want our minimum, so we're going to choose choice number 3, and we're going to answer the same questions. But now I need to move my cursor till I'm to the left of the minimum, which I am, enter. Then I move till my x value is to the right of the minimum, which it is here. And then I move back closer to the min and I press enter. And my calculator gives me the following values. So this will enable me to find my smallest y, because my smallest y is at the minimum. So then this will allow me to answer the range question. So the range is going to be from negative 7.23, I'll round it to 2 decimal places, to positive infinity. So in the homeworks, make sure that you're following whatever rounding rules they tell you to. If I remember correctly, they have you round to the nearest hundredth, but I may be misremembering. So that would answer all of our questions. We have our two zeros, we know where our minimum is, and then the range went from the minimum up to positive infinity. All right, so for example number 3, we're going to be using our graphing calculator again. So let's go ahead and read it. It says, some types of worms have a remarkable ability to live without moisture. The following table from one study shows the number of worms Y surviving after X days without moisture. So we're given some data. So in a lab somewhere, for 160 days, they observed some worms without moisture. They started with 50, and after 160 days, there were 3 worms that were still left alive, and then we have some data in between. So the first thing we are asked to do is plot the data and determine the polynomial that best represents the data. So this is going to be similar to when we did our linear regression. So the first thing we're going to need to do is we press our stats key, and then we're going to choose edit. So that handout from chapter 1 section 4 will be very helpful here as the steps haven't changed. So our L1 is where we're going to put our x's, and our L2 is going to put our y's. So I know right now a bunch of us probably have stuff in our L1 that we would like to have go away, right? So to delete the entire list at a time, if you scroll up into the header on L1 and press clear and then press enter, it will delete everything in the column L1. So make sure that we're using our clear key on L1. All right, so I enter my x values. So 0, 20, 40, 80, 120, and 160. And then I go over to my L2 and I put in 50, 48, 45, 36, 20, and 3. So I got my data input for L1 and L2. And now I want to see what it looks like. So I go ahead and I press graph, and I just see the graph that I had in the previous example. So if I press y equals and clear that out and I press graph again, I still don't see anything. And this is because 2 things. First of all, our plots aren't on, and even if they were, I still wouldn't see anything because I'm on my standard -10 to 10 window. So we need to do 2 different things. First one is we need to turn our stats plots on. So we press second and y equals, and we go down to choice number 5 and choose plots on, press enter. So that's going to turn our scatter plot on. The next thing we're going to do is press window. And we need to change our x-min and our x-max. So I'm going to make my x-min, I'm going to leave it at -10, but I'm going to make my x-max 190, and then change my x-scale to 10. I'm going to make my y-min 0, and I'm going to change my y-max to, say, 60, and then I'm going to change my y-scale to 3. So when I do so, and then press graph, I should now see a scatter plot for my data. So I see my scatter plot, and when I look at this data, does our data appear to be linear? Well, we talked about this a little bit back in chapter 1, section 4, and we're like, well, it's okay at being linear, but it definitely looks like it bends a little bit, right? It's curving just a little bit as it goes down. So let's go ahead and do our regression now. So if I looked at this, I would guess that it's not a line. I think it looks more like a parabola. But let's try a couple of different ones. So if I press stat and I go over to calculate, in the previous sections we always picked linear regression. But notice, what is our choice just below linear regression? It says quad reg, which is for a quadratic regression. So instead of picking linear regression this time, let's pick quadratic regression. We press enter, and now our screen should look the same. So we go enter, 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 and now we get down here. Let's store our regression equation as we did before by going alpha and trace, and we choose y1. We press enter, and our calculator thinks for a second. And this time, it gives us a quadratic. So notice on our screen it says y equals ax squared plus bx plus c, and then it gives us our a, b, and c. So we have those saved into our calculator since we saved it as y1. If I press y equals, we'll notice there's my a value that it saved in, and if I press graph, it will now draw that parabola that goes through the data points. And when we look at that picture, since the parabola curves just a little bit, it looks like it fits those data points a lot better than a line would be able. So we can rinse and repeat this process to find the cubic regression by going to Stat. We go over to Calculate, and we choose Cubic Regression this time. And we hit Enter, Enter, Enter. We go down to Store Regression Equation. Since we stored the quadratic regression as y1, we need to store our cubic regression as y2. So we go alpha trace, choose y2, hit enter, enter, and then this is going to give us this for our cubic regression. Okay, so then having each of those in our calculator, we could then use them to determine the answer to C, which is when will there be 10 worms? So we go to our y equals, we go down to 10 for y3, and we'll notice we have our quadratic regression is in y1 and our cubic regression is in y2, and then y3 is 10. So if we hit graph, it's going to put all three of these on the same coordinate system. So if we want to find our different solutions, we want to find the different intersections. So we've got this guy is y1, and this guy is in y2. So when we go to find our intersection, we go second trace, and we choose intersect, which is choice 5, and it says first curve. And we see the first curve is y1, so I press enter. And I want to find its intersection with y3, which was y equals 10, so I press down to get y3, press enter, and then it says guess. I press enter 1 again. And so it gives me that for the quadratic, we get that the intersection is about 145. So this one is for our quadratic model. And we could do that again with our cubic model. So we go second trace, and we choose our intersection, but instead of y1 this time, we want our cubic model, which was y2. We press enter, and then y3, we press enter, and then guess. And when we do it, we notice the two answers are pretty close, but the cubic model gives us a slightly different answer. But both of them are still fairly close to 145. It's also worth noting that in that menu, there's actually a whole bunch of other ones. So we have cubic, quadratic, quartic, linear, and so forth. So if you keep looking through that menu, you can find other regressions and use them by doing the exact same thing.